Okay, so if you struggle with figuring out rate constant units, hopefully your struggle will end with this screencast. Just a little review of a rate constant. So a rate constant is lowercase k, and how big it is gives you an idea of how fast a reaction occurs. So if it's like 10,000, then the reaction is going to happen pretty quickly. If it's like zero point 0.1, it's going to be a very slow reaction. So it has to do with speed of reaction. Okay, speed of reaction. So let's just talk about how the units vary. So if we look at, let's just start with a zero order. Well, let's just talk about rate first. So rate, again, if you're driving a car, it's miles per hour. It's always going to be something per time. In chemistry, of course, we use concentration per time. And usually it's going to be molarity. And then our time can vary, seconds, meters, hours, whatever. But let's just say seconds for this case. So if we have a first order reaction, so again, keeping in mind rate is always going to be molarity per second for us. And we have first order, there's the rate constant. I'm sorry, zero order. And that's a zero order reaction. So if you have a zero order reaction, that becomes 1, of course. So in this case, our units of the rate constant would be molarity per second, so that we end up with the same units as rate. So if we have a first order reaction, remember rate, always going to be in molarity per second in this example. We have the rate constant times the concentration of A to the first order, so that's a first order reaction. Because the unit of A is going to be molarity, in order for our rate to end up as molarity per second, our rate constant K has to have the units 1 over second. So that would be the rate constant units, and that would be the unit, of course, for concentration of A to the first. So again, you could write the units for K in this case, second to the minus 1. So all we're doing is mathematically trying to figure out how our units of rate are always going to end up with molarity per second in this case. Okay, so let's just take a look at a second order. So again, this is what our product needs to be. So our A squared would be molarity squared. So in order to end up with molarity per second, we would have to have a molarity in the numerator or in the denominator, right? And then a second here. So that molarity will cancel out with that, and we'll end up with molarity per second. So the units of K for a second order would be 1 over molarity per second, or molarity to the minus 1, second to the minus 1. Okay, and you never know, it could be third order. So if we have a third order reaction, again, our rate, always molarity per second, the units. We have K, and let's just make it a third order that looks something like this. A, say B to the first, C to the first, so that's third order. Or it could look like A to the 3, right? Or A to the 2, B to the 1. So regardless, if you multiply 3 molarities together, you're going to end up with molarity cubed. Our units of rate are molarity per second. So in this case, in order for that to work out, we're going to need the units of K, molarity squared, times second. So that cancels out to molarity per second. So if we had third order, our rate constant would be molarity to the minus 2, second to the minus 1. So I hope that helps.